Just look around you for a second. The phone in your hand, the desk you're sitting at, even you. All of it has one amazing thing in common. It's all built on the backbone of a single element, carbon. So what is it about this one element that gives it the power to create the millions of different compounds we see all around us? Let's find out.
To really get it, we're going to follow carbon's story. We'll start with a chemical problem it has to solve, uncover its secret weapon for making connections, and then reveal its two incredible superpowers. After that, we'll look at the amazing things it builds, how it creates almost endless variety, and finally, why it's truly the element of life.
Okay, so first things first. To understand why carbon is so special, you've got to understand its central problem. You see, every atom has these layers of electrons, right? And an atom's main goal in life, you could say, is to get its outermost layer totally full. That's when it's stable and happy. But for carbon, well, getting there isn't so easy.
So here's the puzzle. Carbon has 4 electrons in its outer shell, but it really wants 8 to feel complete. That puts it smack dab in the middle. So what's it going to do? Should it try to grab 4 more electrons from somewhere else? Or should it just give up the 4 it already has and start fresh with the layer underneath?
Well, it turns out both options are pretty terrible. If carbon tries to gain 4 electrons, its nucleus, the core of the atom, only has 6 positive protons. That's just not enough magnetic juice to hang on to 10 negative electrons. But losing 4 electrons, that takes a massive, massive amount of energy. So carbon's kind of stuck. It can't just gain or lose electrons to become a stable ion like so many other elements do.
So what does it do? Instead of all that drama, carbon does something way smarter. If you can't take them and you can't lose them, you share them. This simple, elegant solution is the key to, well, everything. This brilliant solution is called a covalent bond. You can think of it like a partnership or a handshake. 2 atoms each put 1 electron into the pot, and they share that pair. It creates this super strong, stable connection between them. And this becomes carbon's absolute go-to move.
Let's look at the simplest possible example to see how this works. Here are 2 hydrogen atoms. Each one has just 1 electron. They get together, share their electrons, and boom! Now they both get to feel like they have a full shell of 2. It's a win-win. That's a single covalent bond, and it's incredibly stable.
And this is how carbon uses that same trick to solve its big problem. In a methane molecule, you've got 1 carbon in the middle. It takes its 4 outer electrons and shares them with 4 different hydrogen atoms. What's the result? The carbon now feels like it has a full shell of 8, and each hydrogen feels like it has a full shell of 2. Everybody's happy. Problem solved.
But carbon isn't a one-trick pony. It's not just limited to these single handshakes. In carbon dioxide, for instance, it shares 2 pairs of electrons with each oxygen atom. We call these double bonds. This flexibility to form different kinds of bonds is absolutely crucial for the amazing variety of molecules it can build.
Okay, so this whole sharing thing, it gives carbon 2, and I mean 2, genuine superpowers. These 2 properties are the reason, the absolute foundation for why carbon can form this vast, complex universe of compounds.
Superpower number 1 is tetravalency. Now, that's a fancy word, but all it means is that carbon has a valency of 4. Think of it like a Lego brick that has 4 connection points. It can form 4 strong, stable bonds with other atoms, reaching out in all directions.
Superpower number 2 is even more mind-blowing. It's called catenation. This is the incredible ability of carbon atoms to link up directly with other carbon atoms. This self-linking property lets them form these incredibly long and stable chains, crazy branches, and even rings. It's like being able to snap those Lego bricks together endlessly.
So, why can carbon do this when other elements really can't? Well, it comes down to a few key things. First off, it's a tiny little atom, which lets it get nice and close to form super strong bonds. Second, that carbon-to-carbon bond is just naturally really, really strong. And finally, the fact that it can form not just single, but double and triple bonds with itself just adds a whole other layer of possibility.
Let's actually see this in action. Take a look at propane and butane here. You can see how the carbon atoms are just linking up one after another in a straight line. This is catenation in its simplest form, and it creates the backbone for just countless molecules.
But they don't have to be these perfect, straight lines. They can also branch off, kind of like the branches of a tree. This ability to create different shapes is one of the key reasons we get so much diversity from carbon.
And if that wasn't cool enough, the chain can even loop all the way back around and connect to itself, forming these super stable rings. So you've got straight chains, branch chains, and rings. These three simple patterns are the foundation for the absolutely staggering variety we see in organic chemistry.
So, with these superpowers in its toolkit, what does carbon actually build? Let's start with the most basic family of carbon compounds, the hydrocarbons. As the name suggests, they're made of just hydrogen and carbon. Now, we sort these hydrocarbons into families based on the kinds of bonds they have. If a molecule only has single carbon-carbon bonds, we call it saturated. You can think of it as being totally saturated with as many hydrogen atoms as it can possibly hold. Its hands are full. But if it has double or triple bonds, we call it unsaturated because it has room to add more stuff. And then there's this really special class of ring structures called aromatics.
Within these families, you find this really cool thing called a homologous series. Just look at the alkanes here. Methane is CH4. The next one up, ethane, is C2H6. After that, propane is C3H8. You see the pattern? Every time you go up one step, you add exactly one carbon and two hydrogen atoms, a CH2 group. This makes organic chemistry surprisingly predictable and systematic. All right, so carbon can form chains, branches, and rings. But there is one more amazing trick up its sleeve that just explodes the variety of possible compounds into the millions. That trick is called isomerism. It's this wild idea that you can have compounds with the exact same molecular formula, the same set of ingredients, but you can arrange those ingredients in different ways to create totally different things. It's like having the exact same bag of Legos, but building two completely different models. Take a look right here. Both of these molecules have the exact same recipe, 4 carbons and 10 hydrogens, C4H10. But their structures are totally different. On the left, butane is a simple straight chain. On the right, isobutane is branched. And here's the kicker. That different shape means they are literally different chemicals with different properties, like different boiling points. Same parts, totally different molecule. So, when you put it all together, the ability to form 4 bonds, the superpower of linking to itself in endless chains, branches, and rings, and this incredible trick of rearranging its atoms into isomers, you get the ultimate molecular construction kit. This is why carbon is the foundation of all of organic chemistry and, well, life itself. In the end, what's so incredible about carbon is how a few simple rules can create, well, near infinite complexity. It's the element that builds our world. From the fuel in our cars and the plastics we use every day, to medicines and our very own DNA. And with so many combinations still out there to discover, it really makes you wonder, what might the next carbon compound we find be able to do?